up at 12, 24 hours to do it tomorrow at noon. Same format, but again, the last 31 to 35 are bonus questions. We're going to have to do a little bit of thinking, mental effort on some of those, so they're probably not as straightforward as you might think, so they'll take some time and effort looking up the data for them. But we're talking about stereochemistry, and again, a stereogenic center is an atom with 4 substituents or ligands. And then we talked about assigning R or S to them, where each substituent is assigned a priority that's based on atomic number. And for the rules to work, the lowest priority group has to be pointed away from it. So clockwise is R, counterclockwise is S. In some instances, if the lower group is pointed towards you, you still do the same algorithm of determination, but if you then determine it's R, you just flip it to S because it's pointed towards you. So just make sure that the drawing you're looking at how you're figuring the problem out. Again, I can't stress it enough, the easiest way is just to make a model of it and sort of do it the right way. So for every one stereo center, you can have an R and then an S mirror image in the antibody. What we're going to focus on today is building that up. Molecules that are going to have 2 stereoisomers. So how do we then name those things? How do we determine relationships of mirror images? And then what other relationships of stereoisomers are present? And then hopefully there's enough time, we'll look into another form or drawing of looking at these called the Fisher projection. And that allows us to determine if things are mirror images pretty easily. So we'll talk about these different drawing conventions, sort of the flat, then the Newman, and then the Fisher at the end. Any questions before we dive into it? So what we'll start with is just picking up where we left off with butane. So, with C4 is the lowest carbon count that you can have. Once you stick another sort of heteroatom in there, that's going to generate a stereo center. So we're going to build up from that. We're going to put 1 in, then we're going to put 2 in, look at the relationships. And again, it can get pretty complex as you increase the number of stereo centers. But the logic still applies. So there's butane. We've done this exercise quite a bit now. How many unique sets of hydrogen does butane have? So the answer is 2. And what I want to point out is this drawing convention that we use, with just these lines. Typically things are drawn in this zigzag, which I think is formally called Ziegler-Natta. So if you're a polymer chemist, you can say I talked about polymer chemistry in this course. It's just the way of representing the zigzag. And the reason it's done that way is because C1 and C4 end up being anti to one another when you're looking down that Newman projection of 2 to 3. So in a way, you're drawing the most stable conformer of that chain. The other thing that I want to point out just briefly, I won't dwell too much on it, is sort of the art of organic chemistry. So if you notice, C1 and C3 are down, C2 and C4 are up. So let's focus on 2 and 3. When we're putting in wedges and dashes, you want to make sure that you sort of represent the bond angle of an sp3 hybridized carbon faithfully. So if we want to put a wedge and a dash at C2, I'm going to draw the wedge coming out towards you, but these bonds have to be up. I mean, they have to point to the top of the molecule. So we would draw a wedge like that, and then a dash like that. At C2, or excuse me, C3, since that carbon is down, those bonds have to be pointed down. So that would be a good representation. Picasso would be happy with that. So for example, what you don't want to do is the following. So for example, at C2, you wouldn't want to put like that. Or at C3, just because it sort of looks weird. I know it's picky, but if you're making a model and then you sketch that model, the top drawing is more accurate than the bottom one. And the more faithfully you draw these things that resemble the hybridization and bond angles, I think your understanding will be a lot better. So that's a word about the drawing. The answer here was B. There's two sets in a 6:4 ratio. You'll see some of that on the exam today as well. So this question states you have two sets, and then you're going to swap out a hydrogen for a bromine in each set. And then what's the total number of constitutional and stereoisomers? So what that means, so at C1 or C4, we have 6 hydrogens that are equivalent. We swap one out. So that makes 1 bromobutane. Now, if we do the same thing for C2 or C3, that makes 2 bromobutane. But we further recognize that carbon 2 is a stereocenter. So then we can really draw that as the R and the S enantiomers. So overall, we would end up with 3. And again, I'm not just whistling Dixie here. The point of that exercise is when we get into Module 4 on Friday, the first reaction you're going to learn is CH substitution, where you're taking a hydrogen atom and you're substituting it for a halogen. And so that's a pretty fundamental reaction where you take a nonpolar molecule and it then becomes polar. And the issue is, based on the reaction conditions, how do you know where the substitution is going to occur? To answer that, you really have to draw out, these are all the possible products, and then this specific one is preferred. So let's review the priority assignments, and then we'll assign R or S to these enantiomers. So again, they're mirror images. The one on the left is the wedge. The one on the right is the dash. And so let me just draw in the H, which is now pointed back. That's the lowest priority group. So that's 4. Then you have a bromine, a carbon, and a carbon. Bromine's going to win, so that's 1. Now the issue here is carbon and carbon. So how do you assign priority? based on the quiz from last time. In the first step, you're only going out to the directly bonded atoms. If they're equivalent, then you have to go out to the atoms bonded to them and apply the same question or test. So since they're carbon, the one on the left, so C1 has 3 hydrogens. And I'm just going to put the atomic number, so 1, 1, and 1. Carbon number 3 has 2 hydrogens and a carbon at C4, so that's 1, 1, and 6. So that carbon, since it has a higher priority element bonded to it, is going to get priority 2. That will be 3. So overall, we're going clockwise here, so that will be R. And then we'll just do it for the other one so you can see what I mean by, now that hydrogen is pointed out towards you. So remember, the rules state the lowest priority has to be back. So it's still 1, 2, and 3. So you'll notice you're still going clockwise, but since that's towards you, you figured out it was R, you just reverse it to S. But once you figure out a stereocenter for 1 carbon, the mirror image has to be the other one. So this is where we're going to sort of increase the learning curve here. We'll take a note, 1 stereocenter. So 1 stereocenter can be R or S. Now, what if you have a molecule with 2 stereocenters? How many total stereoisomers can you have? So we'll just work it out on here, but there's a slide that shows it coming up. So remember, 1 stereocenter can be R or S. If you have 2 stereocenters, you could have RR, they're both R. The mirror image of that is going to be SS. So what you have to visualize in your mind is, these letters are corresponding to something on a molecule. So even though it's just like a simple letter, it's representing something in an actual molecule. So the other combinations you can have RS, and then its enantiomer SR. So that's going to give you a total of 4 stereoisomers. When you're looking at a molecule, the stereogenic centers can be anywhere. So you really have to look at every carbon, apply the test. However you're asking the question for that test. For like a methylene group which has 2 hydrogens, you could say, does it have 2 of the same group? Yes or no? Or you can ask, are all 4 groups different? Whatever way helps you think about it. So here's a table, and I wrote some numbers in to continue it on. One stereocenter gives 2 stereoisomers. 2 stereocenters gives 4. How many do you think 3 stereogenic centers gives you? I heard a 6. That's not quite there. I heard an 8. I heard a 9. It's going to be even. So it's going to be 8. What do you think 4 gives you? 16. And then of the responses shown, what do you think the rule is for n stereocenters? It's going to be 2 to the n. So whenever you determine the number of stereocenters n, you have a possible of 2 to the n maximum stereoisomers. But there's a sort of catch to that we'll see today with the model kit and some of the slides. Even though 2 to the n is the maximum, you don't necessarily have that number. There's another issue that arises. But that's a good jumping off point. So it's 32 ... 2 to the n. So here is, for n equals 1, 2, and 3, the 2 to the n number, and then the possible stereochemical configurations. So we said that for 1, you get 2 possible stereoisomers. They're either R or S. And then hopefully you can see the logic moving from n equals 2 to n equals 3. I don't know what are these combinations or permutations. Anyone that's taken stats can correct me. The easiest thing to start with is just make them all the same. So RR, and then its enantiomer SS. And then when you're figuring out sort of the next line or however you want to think about it, you just change one of them. So n equals 3, you have R, 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 S, S, S. So again, mirror images are enantiomers. And the designation has to be exactly opposite. But what about of these 4 here? So RR and SS are enantiomers. What about the relationship between RR and RS? What's their relationship? These are called diastereomers. Since it starts with di, I just think different. So again, the challenge for you is looking at the letters. It's straightforward in a way to tell if they're enantiomers or diastereomers. But the work really comes in when you're given a drawing, and then you have to figure out if they're enantiomers or diastereomers, because organic chemists, being the people they are, things are never presented to you in sort of one way. And so that's why you have to be comfortable looking at sort of the zigzag drawing, the Newman projection, and then the Fisher projection we'll learn a little bit later. So the model kits help with that, and then as you use them, you sort of become fluid in your mind of, okay, I can sort of flip or I rotate a bond, the whole molecule, that sort of thing. So what's a good way to say this? I think for any n, you're always going to have n pairs of enantiomers, but then the number of diastereomeric relationships will be greater. Is that right? Equal or greater. Let me put that in there to save my butt. So let me draw that in maybe blue. So those would be diastereomers. Those would be diastereomers. Those would be diastereomers, and then those as well. Any questions? So I've sort of stripped down this problem in the sense that I'm going to funnel you into, you have a question?
If it's all SS, it's going to be an A.
Yes. So I've stripped down this prompt here. We're going to start with 2-bromobutane, and then we're going to add a second bromine. But we're only going to do it at carbon 3 because that's going to generate a second stereocenter. If you put it at 1 or 4, those carbons do not end up being stereocenters because they each have 2 hydrogens bonded to them. And so the sort of parent name of this would be 2,3-dibromobutane. And so C2 and C3 are both stereogenic. Maybe one thing to point out, a trap you don't want to fall into is, when you're looking at a carbon and doing the test for if it's a stereogenic center or not, you're looking at the directly bonded atoms, but sort of don't get too focused on that. Look at the rest of the molecule as well, just so you don't eliminate one by mistake. So there it is. So that carbon has a bromine, a methyl, a proton. And the way that I think about it is this whole thing is unique. So that's a stereocenter. This carbon has methyl, bromine, hydrogen, and that whole thing, which is unique. So we have 2 stereocenters. So 2 to the 2 stereogenic centers, 4 possible stereoisomers. So again, this is the substrate or the model compound that has an issue. Even though there's 4 maximum stereoisomers, what we'll see is that in reality, there's only 3. And so that's going to require looking at the model and doing a little bit of sort of mental gymnastics. So I've drawn them out here for you. The top line is 2R, 3R, and that's the nomenclature for this. Is you have the location and then the CIP designation of what that stereogenic carbon is. So its enantiomer has to be 2s3s. And notice what I did in the drawing. These aren't exactly drawn as mirror images, but I made the wedges into dashes. And so just by flipping that around, it changes the R to S. The second pair here, I left carbon 2 as R. Carbon 3 I drew as a dash. So because we determined R up here, we're drawing it the opposite way. It has to be S. And then over here, for the mirror image, I made the wedge to a dash, the dash to a wedge. But look at the names. Does that seem weird to you? So if this compound to the right was a true enantiomer, this should say 2R, or no, excuse me, 2s3R. But notice how they have the same designations. So what I hope to convince you of is these are actually the same molecule. So they're identical. They're not mirror images. So before we get into it, maybe one thing I can point out. So I drew a dot in between carbon 2 and 3. Now, if you imagine putting an axis through that dot and rotating it, can you see how the one on the left becomes the one on the right? If you do the same thing for the compounds up top, I'll do that in blue. If you do that same rotation, you will see that the bromine atoms do not line up. So even though we said there should be 4 real stereoisomers, this one only has 3. So a check-in question here. What's the relationship between 2R, 3R and 2R, 3S? So notice you're not given any structures, but if you understand the logic, you'll see that since one stereocenter is different, they have to be diastereomers. So this is not a trick question. The relationship between 2R, 3R and 2R, 3R is they are identical. So 2R, 3R is equal to 2R, 3R. But you're a student. Think about if you were teaching this class and writing an exam. Another way of presenting this question to you is if it was in structure form. But the structures are not drawn the same way. So you're going to have to do like a flip or a bond rotation or something like that. So this is probably the most straightforward way you'll see that concept presented. So the green arrows so enantiomers, and then the question mark on the bottom one, are they really enantiomers? No, they're not. They're identical. The blue arrows indicate diastereomeric relationships. So again, you either look at the CIP designations or you sort of draw them in the same format and look at the wedges and the dashes. Are they mirror images to one another or not? So I don't think I need to belabor this slide anymore. So it says, notice the supposed bottom set of enantiomers has the same name. And again, that's this designation here. If you put that dot and rotate it 180 degrees, you see they exactly map onto one another. Another way that is used to determine sort of this issue really helps to use a model kit. So let me flex it around here. Make sure I have this. I want to do that one. So the one on the left. So when I talked about the zigzag, so this is carbon 1, this is carbon 4. So this is down, then this is up. And when I talked about a rotation, I don't want to rotate it. Let me do it so I don't do too much at once. So let's look at this right here. So I'm going to take this bromine and rotate it so that instead of these methyl groups being anti, so in the Newman projection they're anti, I'm going to rotate it so they're eclipsed. So the dihedral angle is 180. Now this dihedral angle is 0. So the methyl groups are eclipsed. So notice when I do that, this bromine is towards you, this one is away from you. When I do that, they're now both towards you. The same thing will happen over there. So if I just take this and then rotate it, see how they're both back now, which is the one on the right. So that means they have to be the same thing, because all we've done is a rotation. What you absolutely cannot do, if your hand starts swapping things out, that's not allowed. So you can't swap anything, you can just do like rotations and flips. So aside from the rotation argument, so it's that, or you rotate it, it's the same thing. Even though this has the two stereo centers, this is a special type of compound called a meso compound, so MESO. You have a stereogenic carbon, and now, just like your body, if you slice it in half, if you slice this in half, this mirrors this, the hydrogens mirror, and then the methyls mirror one another. So a meso compound is a special stereoisomer. It must have stereogenic centers, and it must have an internal plane of symmetry. So that would be a mirror plane. Yeah. So meso compound has stereogenic centers, but when I say achiral, what I mean by that is if you put this molecule in a polarimeter, the specific rotation is going to be 0. So again, the way I think about it is maybe the R stereo center rotates it to the right, the S rotates it to the left, and overall you get 0. So let me write that down. So this circle here just means a bond rotation. Again, you're not allowed to swap atoms out. You're only allowed to do like twists or flips and stuff. So if you were to study this for more than 2 semesters, you'd start seeing patterns in these things. And you could probably do it without a model. But to facilitate your learning, there's another type of projection that's used. It's called a Fisher projection. So remember, a Newman projection, you're looking down a sigma bond. A Fisher projection, you're looking at the molecule a different way. And the reason this exists is to help you determine relationships. Are they enantiomers or diastereomers? Because you're sort of putting them all into one form, and then the comparison is easier. So I always, pepper these slide decks with a little bit of historical information. So Fisher won the 2nd Nobel Prize in chemistry for his recognition of services rendered to his work on sugars and purines. If you take organic 2, those are things we'll talk about, biomolecules in organic 2. If you don't take organic 2 and you just go into like cell and molecular biology, they'll talk about it as well. Those are the molecules sort of in your body. And one of the things that's always fascinated me, and you have the textbook, you can look it up in the carbohydrate chapter, is Fisher's proof of this molecule here, D-glucose. So you've most likely heard of glucose at some point in your life. That's the structure. And a carbohydrate, what the name means is for the formula CH, you have a certain number of H2O. So really all it is, it's a carbon backbone with a lot of alcohols on it. So you can see that glucose is 1, 2, 3, 4, 5. It's a 6-membered ring. And then what do you notice about all the substituents on it? They're equatorial. So that's kind of neat, right? If nature chose this molecule as sort of our food source for living organisms, all these substituents are equatorial. They're the most stable arrangement. So this has 1, 2, 3, 4, 5 stereoisomers. So Fisher was the first human being to walk this planet that assigned that exact structure, and he got it right for those stereocenters. And he developed this tool of the Fisher projection to help figure that out. So I need to do some arranging here. Okay, so I'm going to use the yellow ones now as the methyl groups. So carbon 1 and carbon 4. And then we have these blue hydrogens, which are pointed towards you, and then the red hydrogens are pointed back. And so you're looking at, again, the zigzag. So here's the drawings in this plane. Your eye is 90 degrees to the plane. When they do a Newman projection, so where it says anti-conformer, all we're doing is we're just rotating that way. And you can see the red hydrogens are on the left, the blue hydrogens are on the right. And then in the bottom sort of scheme, what am I going to do? I'm going to take this hydrogen, or excuse me, this methyl group. And instead of them now being anti, they're going to be eclipsed. And so notice the color change. So you have to do that. And now, so there's the eclipsed conformer. So you have red, blue, blue, red. So the Fisher projection, the backbone is eclipsed. It's no longer anti. And then in terms of the mental gymnastics, now you're looking at the Newman, and you're going to rotate that 90 degrees. So instead of looking down that sigma bond, your eyeball is going to be here, and you're just rotating it like that. So we have blue, red, red, blue. But again, and this is always tough for me to figure out. I'm holding the carbon backbone. These carbons are now close to one another. So this is the Fisher projection. So these groups are coming out to hug you. They love that you love organic chemistry. You see how in the middle there, they're represented as the wedges? But that's further simplified to the top right, where they're just lines. But again, if you think about a line being in the plane, it's just done to, I guess, make it easier to draw across. But they're coming out towards you. So that center bond in the middle there between 2 and 3 is in the plane. That top bond, even though it shows it's pointing up, see how it's actually going back? So again, the models will help you understand what the Fisher projection is telling you. And so in the bottom one here, that was the true set of enantiomers from that 2,3-dibromobutane. So we have 2R, 3R, 2S, 3S. So again, here's the zigzag. What has happened is a rotation. And then you're putting your eyeball like right here, looking at that bond. So again, what is sort of challenging is, in this way of drawing it, the bromines are on the same side. But once you rotate and look at it from the Fisher projection, they're on opposite sides. You do the same thing for here. You can see that that's the exact mirror image. So I when talking about Fisher, I just say left, right. And now you have right, left. Any questions? You will maybe thank me that you have 24 hours to do the exam. If you are sitting in here for 60 minutes trying to figure out R or S from a Fisher projection, your head would start smoking. Again, because the challenge is, see how those are drawn flat? But really they're coming out towards you. And if you're trying to put the lowest priority group away from you, it ends up being like out here. I mean, you really have to, in your mind's eye, do some rotations to get your viewpoint correct. So my advice is, anytime you see a Fisher projection, just make a model of it so you can grab that hydrogen and sort of look at it however you want. And so this is where the Fisher projection pays off, is that other set, which is the identical compound. When you draw it, convert it into the Fisher, you can see that mirror plane pretty easy. So there's the internal mirror plane right there. And before we move on from that, so this is the Fisher projection to the right over here. Again, the methyls are back. In a Fisher projection, really the only thing you can do is this. So you see when I did that, I now make this one over here. So they're the same. Again, what you cannot do is start swapping things. So if you try to do that, you're going to get the wrong answer. So you can do a 180 rotation. You can't do like a 90 because that will screw things up as well. So there's some nuance to using those models as you analyze the problem. So the Fisher projection, again, you know, if you were drawing these out, so if you had all three of them lined up like that, you could then easily tell, okay, these first two have to be enantiomers because they're mirror images. Those have to be diastereomers. Those have to be diastereomers. So visually, again, of these two, see how they're the same? But then this stereo center you're flipping. So that tells you they're diastereomers. So while on it here, remember that enantiomers have the exact same physical properties. The only thing that changes is the specific rotation, the sign of the specific rotation. Diastereomers can have completely different physical properties. So again, if an enantiomer and two enantiomers, if their melting point is 49, they're both 49. But if they have a diastereomer, it can be anything. And you just have to look that value up.
So how would we assign priorities to the Fisher? Or would we do that before we draw it? Or?
So, for example, I'll do it in blue here. So here, the bromine is still 1. Hydrogen's 4. We said that carbon was 3, and then that carbon was 2. Now again, what's challenging about this the horizontal bonds are coming out towards you, the vertical bonds are going away from you. So, even though we determined 1, 2, and 3, what is that? Counterclockwise. That H is coming towards you, right? So if it's counterclockwise, you have to reverse it. That should be R, so that's 2R. That's what's tough about the Fisher projection, in my opinion. So it's easier to build a model, and then so you can rotate things into sort of the normal form. There's a question up here.
The definitive drawing is the one in the cardinal and decimal count?
No, these are the same compound. So this and this are identical. So overall, yes, the compound itself is meso. The one, okay, yeah, so this one right here is the meso compound. These other two are not. So in the time we have remaining, we'll look at another case of this that's a little bit more biologically relevant, and how we can connect, the zigzag to the Newman to the Fisher projection and sort of move back and forth between them. And this has to deal with a molecule called tartaric acid. So there's 4 carbons. At carbons 2 and 3 are alcohols. So this is 2,3-dihydroxy. Butanoic acid isn't exactly correct. It should be like dibutanoic acid. Because at carbons 1 and 4, there's 2 acids. So it was extracted by Scheele in 1769. And then sort of prior to that, as I mentioned about, people studying light, Huygens observed double diffraction of light through this material called calcite. So basically shining light through it and expecting it to go out one way, but it was coming out another way. And so that was like, okay, that's weird. How do we explain that? This was further confirmed in 1811 by this gentleman, who I assume is French, and I'm not going to butcher the name here. But presumably that person theoretically described plane polarized light in mathematical terms. So remember that plane polarized light is dealing with like math and vectors and physics and whatnot. And so in 1832, a sample of tartaric acid was observed to rotate plane polarized light. And so through these, you can see how long these things take to evolve, right? A couple hundred years. And then a name that we're pretty much all familiar with, Pasteur, when he got hold of some solid tartaric acid, he noticed under a microscope that there were mirror image crystals. And so he used tweezer and scalpel to separate them, put them in a polarimeter, and noticed that they rotated the light in opposite directions. And so, again, all of that now is reduced to fact, which is in your textbook. But, think about if you're in their place in 1690, other than your like dirt hut, what do you have to do scientific research? So a lot of science just comes from simple observations, and you don't have to be trained as a scientist to make these observations. You're just asking questions. So the same deal here. We're just shuffling some functional groups around. Tartaric acid has 2 stereocenters. So you could get a possible 4 stereoisomers, but if you're thinking about what we just studied with the 2,3-dibromobutane, this is the same case. The acid groups at 1 and 4 are the same. Yeah.
Will we have a question like this on our exam?
There will be Fisher projections on the exam.
But like, will it say how many total stereoisomers? The answer is 4, but there's actually only 3. Like, would we say the answer is 4 and be
No.
right, or would we say the answer is 3 and be right?
The question that's on the exam, it's the exact answer. So whatever the theoretical max is, that's the right answer.
Okay, so 4.
Correct.
Like in this instance.
Yes.
Okay.
So here are those stereoisomers drawn out. You'll see that the 2 on the left are enantiomers. They have opposite CIP designations, but these 2 here, again, notice the same deal. Those names are the same, so that's an identical compound. So in this case, you're not really doing a rotation, I guess. You would do a flip. Flip and a rotation, making pancakes here. But these 2 end up being the same thing. So we got 2 minutes. We're going to use it. Remember at the start of the lecture I said carbons being up or down. From the zigzag to the Newman, that can sort of help you in terms of where you're putting these wedges or dashes on what side in a Newman projection. So if you have blue eyes, this is your eyeball looking down carbon 2 to 3. That acid has to be down. This acid has to be up. So overall, they're anti. See how these are both back? So if your eyeball was here, hydrogen would be out, hydrogen would be out. So the OH groups should be on what side, the left or the right? The what? The left. So we would get A as the response. So if that is challenging for you, again, the model kit will always help you get it right. So since you're looking down this bond, that acid has to be down right here, and then this acid has to be up right there. These are on the back, so relative to your eye, they're going to be on the left. So this slide helps you convert, the zigzag to the Newman and then draw the enantiomers as shown by the dotted arrows where your eye is looking. Any question?
Yeah, so I was just wondering, because if you're looking down this way, how do you know which one's going to be at the very top? Because there's 2 that look like they're on the top.
I know it's a minute or 2 over, but this is how you take the Newman projection. You have to do the bond rotation to get the eclipsed conformation. And then you rotate your eyeball so that you're looking at the 2 to 3 bond right here. And that's how you draw the Fisher projection. So the remaining slides just explain that a little bit more. I'll post this onto YouTube as a review, but you have a quiz and exam both due tomorrow.